Generating a video from a single image sounds simple, but in practice it is extremely hard. Most models that try this end up producing blurry videos or motions that feel fake and rubbery. And the reason is simple. Predicting motion directly in pixel space is fundamentally ill-posed. When a model predicts pixel trajectories, it has to choose one feature out of many possible ones. So what does it do? It averages them. That averaging destroys sharp motion and produces oversmoothing. Even powerful neural networks struggle here because pixels themselves are a very poor representation of motion. Instead of predicting pixels, we should ask, how does motion actually behave in the real world? If you look around you, a lot of natural motion has structure. Leaves moving in the wind, cloth fluttering, water ripples. These motions are not random. Their energy is mostly concentrated in low temporal frequencies, with higher frequencies being weaker and noisier. So rather than predicting where pixels go, we predict motion in the frequency domain. What we predict is a motion spectrum. Think of it as a map of Fourier coefficients for horizontal and vertical motion at each spatial location. This gives us a spectral volume that describes how motion evolves over time. Once we have this spectral volume, rendering a full video becomes a deterministic process. The hard part is generating that spectrum correctly. To generate motion spectra, we use a latent diffusion model. First, a variational autoencoder compresses the input image into a latent representation. Then, diffusion adds noise and iteratively denoises it. Latent diffusion is ideal here because it can model complex high-dimensional distributions efficiently without operating directly in pixel space. But there is a big challenge. If we predict all frequency components together, they mix and motion becomes blurry. If we predict each frequency independently, they become uncorrelated and motion looks physically wrong. Each motion needs partial correlation across frequencies, not full coupling and not full independence. To enforce this, we use frequency attention. Spatial layers handle spatial structure and frequency attention layers allow frequency bands to communicate, enforcing realistic coherence across motion components. Finally, frequency magnitudes can be unstable. So we apply frequency adaptive normalization using dataset level statistics and compress dynamic range with a square root nonlinearity. This stabilizes training and prevents a few dominant frequencies from overwhelming the model.